We have been some problems with the system, so if my computer screen disappears at any time, don't be afraid to give me a yell and let me know. We've been having some disconnection issues with the content. So anyway, we have been looking at these solutions, the dilutions and all that, and we started talking about dosage calculation, the dosage calculation formula last week. We're going to talk about a little bit of both of those right now and then tie it into more dosage calculation processes. First thing I want to talk about is constituting a formula. So constituting a solution for medication. Many of our medications will come in either a powdered form or they will come in a vial. If it's liquid, with just a small amount of liquid in them, and that liquid is the medication. The reason they're sent that way is to save on shipping costs and shipping weight. Why would you ship water and pay for that extra weight when you can just ship the medication? So in order to use that medication, right before you use it, you'd use that needle the syringes we talked about last week. You would fill it to the appropriate amount of saline or sterile water, and you would inject that into that solution to fill it up and mix it to constitute that solution. So as we look at the labels, one of the things with our dosage calculation is going to be, it's very important to pick out the correct information from the labels. So a label might say, constitute to 120 milligrams per milliliter with 4.5 milliliters of sterile water. Well, there is a lot of information here. The first is you're going to have to add 4.5 milliliters of sterile water, or our normal saline that we've been calling it, to that vial to finish this solution. But as far as constituting this solution, that's important to pick out. But as far as calculating our dosage, the important information here is this right here. 120 milligrams per milliliter. If you go back to what we talked about ratios and rates, that is a rate. And rates can always be used as an equivalency for making unit conversions, interdimensional analysis. So that rate of 120 milligrams per milliliter, remember that means that really represents 120 milligrams over 1 milliliter. It can also be thought of as being an equivalency, where it is telling us that 120 milligrams of medication is equivalent to 1 milliliter of that solution. And that is a rate that's going to be very important for us as we make our calculations in our dosage calculation. So we left off last time. We had mentioned that dosage calculation formula. And our dosage formula consisted of the doctor's orders divided by an on-hand dose times a vehicle equals the amount to administer to the patient. And the keys were that the doctor's orders and the on-hand dose had to be the same units. If they're not the same units, it requires us to do some sort of conversion ahead of time. The vehicle is what carries that on-hand dose H into the patient. It might be a certain volume of fluid. It could be a tablet, whatever it is, whatever vehicles being used to carry that medication from the bottle or vial into the patient. So our example of that, let's say the doctor's order calls for 1,000 milligrams of medication, of pain reliever. And we look at the label. And our label says 300 milligram scored tablets. So the 300 milligram tablets is the important part there. But the scored does have significance. What that scored means is that those tablets, and I'm sure you've seen them, have a line across them, an indentation across them, where they're partially cut through already. What that is made for is so you can just take a medical spatula or whatever and press there, and it'll easily split that pill into two pieces that are very, very close to equal. So when we have that word scored in there, that means we are going to round to the nearest half a tablet. Now that part, rounding to the nearest half tablet, that involves whatever method we use for calculating the dosage. If we have scored tablets, whether it's this formula, whether it's a proportion or dimensional analysis, as we see them later. So anyway, the doctor's order here is the 1,000 milligrams. The on-hand dose is that 300 milligrams. Notice again, the units have to match. The on-hand dose has to have the same units as the doctor's orders, or the formula doesn't work. The vehicle, well, what carries that 300 milligrams to the patient? That is a tablet, one tablet. And that's going to equal what we have to administer. Now, we divide out, of course, the milligrams cancel. 1,000 divided by 300 is 3 1/3. Note that's unitless because the milligrams cancel out. 3 1/3 times one tablet is 3 1/3 tablets. Now, we said we have to round to the nearest half a tablet. So we're going to think about this. We have 3, 3 1/2, and 4 tablets. If we're looking at it on a number line, rounding is saying going to the nearest half tab. 3 1/3 is right here. That is closer to 3 1/2 tablets. So what we would administer is 3 1/2 tablets. Now, a lot of people say, but that's more than what the doctor ordered. And that's a very good point. There are some medications that you do have to check, safe dosages and stuff like that, which we'll talk about later on what is a safe dosage of a medication. So you would have to double check to make sure that that rounding up does not put you above a safe dose for that medication. Most medications have a pretty big buffer zone where you're not going to run it. Like most of your over-the-counter medications, the safe dose is more than double what the recommended dose on the label is. Okay, so similar to that, let's say we have a problem where the doctor orders 400 milligrams of medication, and the label on our bottle or vial says that this is 50 milligrams in 4 milliliters. So for our dosage calculation formula, the orders is a 400 milligram. So that's our doctor's orders, D. The on-hand dose, well, this is 400 milligrams in 4 milliliters, or sorry, 50 milligrams in 4 milliliters. So 50 milligrams is our on-hand dose. Times the vehicle. Well, that 50 milligrams of medication is carried into the patient in 4 milliliters of fluid. So that's just the math. The milligrams cancel. 400 divided by 50 is 8. Again, that 8 is unitless because the milligrams canceled out. 8 times 4 milliliters is 32 milliliters. So you would administer 32 milliliters of that medication to our patient. So that is the dosage calculation formula. To me, that's the least desirable method of doing dosage calculations, but it is there. And for some people that are going to have to do just basic calculations like this, it's adequate to get them through. If you're going to have to do a lot of medications with IVs and anesthesia and other calculations of dosages rather than just these basic, how many tablets and how much of a fluid to administer, if you're going to do much of that more complicated stuff, then the dosage formula is probably not the way to go because there are several other formulas that have to be memorized for each of those other situations. So the next method I want to talk about is the proportion method. The proportion method for calculating dosages has a couple of strengths. The one strength is you don't really have to memorize anything. You just match up units. It also has a weakness. The weakness is it may need to be applied several times. So it may need several steps in a problem per situation. So let's take a look at the actual proportion method. What the proportion method tells us to do is we take the information on the label and we're going to use that then to relate to the doctor's orders and what we're going to administer. So for example, if we use the terminology of the last thing with the dosage formula, you get off the label, you can read off the on-hand dose in the vehicle. That's usually a ratio, as we've seen. Well, the on-hand dose will have the same unit as the doctor's orders, and the vehicle will have the same units as what we administer to the patient. So the result that we're looking for is this bottom number in our second ratio. Now, we don't necessarily need to memorize that setup of H over V equals D over A, because the units will tell us how to set it up. Let's go back to that first problem we had. Our orders are for 1,000 milligrams of medication. Our label is 300 milligrams scored tablets. So 300 milligrams scored tablets is a ratio. That is 300 milligrams, actually it's not a ratio, it's a rate, 300 milligrams per one tablet. And now we can use that rate, that's our label information, to relate to the doctor's orders and what we're going to administer. Well, the doctor's orders are for 1,000 milligrams. That has to match up with the milligrams. So what we get down here is what we're going to administer to the patient. The units that has to have is going to be the same units as over here, tablets. So we now cross multiply and divide. 1 times 1,000 is 1,000 divided by 300 is once again 3 1/3 tablets. Now that's scored, which means we round it to the nearest half, which is 3 1/2 tablets. Or we could have our second example up there, The doctor orders 400 milligrams of a medication, and our label says it is constituted at 50 milligrams in 4 milliliters. So again, we have our label information. 50 milligrams in 4 milliliters is a rate. So we set up that rate. Now the other rate in this problem has to match up the units. So we know this is going to have to be milligrams, this is going to have to be milliliters, because those units have to match up. The doctor's orders is 400 milligrams, so that has to go here with the milligrams, and we'll cross multiply and divide. 4 times 400 is 1600, divided by 50 is 80 milliliters. Oops, what did I do wrong there? Yeah, that's right, 80 milliliters. So we have, oops, let me punch in my calculation. 32 milliliters, there we go. I knew the internal calculator wasn't handling that one quite right. 32 milliliters is what that ends up being. So 32 milliliters is what we administer to our patient. Now I said there's weaknesses in this whole formula, the proportion. And what that would be is if we run into something like this, where a doctor orders 5,000 units of a medication. So if we look at the label, and the label tells us it's 1,000 units in 20 milligrams and constituted with 5 milligrams and 2 milliliters. If I wanted to use either the dosage calculation formula or the proportion here, I'm going to have to do this twice. I start out with a rate that has what the same units as my doctor's orders. The doctor's ordering units. Now, unit is a medical term. It's actually a specified volume or portion of a medication. So we have 5,000 units. Oops, sorry. I got 1,000 units is off my label in 20 milligrams. So that's my labeled rate. And I'm going to use that with my doctor's orders of 5,000 units. And what I'm going to end up with down here is milligrams. And I cross multiply and divide. 20 times 5,000 divided by 1,000 should give us 100. I missed a zero there. That would be 100 milligrams. So we have 100 milligrams is what needs to be administered to the patient to get him the 5,000 units. But we're not going to administer it in milligrams. We have to administer it. I'm assuming this is a fluid drug since it's in 5 milligrams and 2 milliliters. We have to administer this as a liquid, so we have to do another conversion. So we have to set up a new proportion using this rate of 5 milligrams to 2 milliliters. And we apply things again. Well, we know that the doctor's order was 100 milligrams. That's the equivalent to that 5,000 units. Of course, this is going to end up being milliliters down here. We cross multiply and divide. 2 times 100 divided by 5 gives us that is 40 milliliters that we administer to the patient. So you can see there's one of our weaknesses of that proportion, and we'd have the same issue with the dosage formula. We would have to apply it twice in a situation like this. Which brings us to our last method, which is my favorite method. if you haven't picked up on that yet by the way I talk about it. Dimensional analysis. Dimensional analysis is just an extremely powerful tool. Like an example I gave you before, where we're calculating with any sort of rate. Let's say that we want to know working at $12 per hour, how long does it take to earn, let's go $420. Well, we start, this is a rate, $12 per hour. Remember that rate can be used as an equivalency. $12 is equal to 1 hour. So that's going to be one of our conversion factors. So we're going to start out with the $420. And we're going to make it a fraction by putting it over 1. And we're going to use that conversion factor, that equivalency of $12 equals 1 hour. Well, we're going to put dollars on bottom so that they'll cancel out. So $12 is equivalent to 1 hour. Now what's going to happen is the dollars will cancel out and we're going to be left with hours. So 420 times 1 hour is 420 hours. 1 times 12 is 12. 420 hours divided by 12 is going to give us 35 hours. Now again, many of you knew that you would just take the dollars, the total dollars, divided by your dollars per hour. But if you didn't know that already, the units tell you exactly what calculations you have to perform. So in the medical fields now, this is a powerful tool. When we look at a problem like we had up above there, let's look at each of those examples. So our orders again, 1,000 milligrams. And our label of 300 milligrams scored tablets. Well, when we look at this, we need to think of that as the equivalency. That means 300 milligrams of medication is equivalent to 1 tablet. Or the other way around might make more sense. 1 tablet is equivalent to 300 milligrams of medication. Now we're going to start out with the doctor's orders, and we're going to proceed to what we need to administer. And that's how this always works out. We start out with the doctor's orders, and we convert it using that dimensional analysis to what we are going to administer to the patient. So we'll start out here with the doctor's orders of 1,000 milligrams. We make it a fraction by putting it over 1. Our equivalency, 300 milligrams equals 1 tablet. Well, the doctor's orders are 1 milligram. That's what we're getting rid of. So milligrams go on bottom here. It's going to be the tablets on top. 300 milligrams is equal to 1 tablet. So now the milligrams cancel out, and we just multiply across here. 1,000 times 1 tablet is 1,000 tablets. 1 times 300 is 300. 1,000 tablets divided by 300 is 3 1/3 tablets. Now again, that is scored tablets. We round that to the nearest half, which is 3 1/2 tablets. Always starting out with the doctor's orders, and then just using those equivalencies from the label to get to what we have to administer from the patients. One of the difficulties that some people have with the proportion method is trying to figure out what you start with. So that's one of the other things that's convenient about dimensional analysis, is when we're doing a dimensional analysis, we always start out with the doctor's orders. Let's look at the other example. Our doctor orders, what was 400 milligrams of medication, and our label stated it was concentrated at 50 milligrams in 4 milliliters of fluid. So again, we think of this as being an equivalency. That's 50 milligrams of medication is equivalent to 4 milliliters of the fluid. And now we start by setting this up with our doctor's orders, 400 milligrams over 1. Then we try to convert from there. Getting rid of milligrams, so milligrams go on bottom here. We have 50 milligrams is equivalent to 4 milliliters. So the milligrams cross cancel. Now I get asked all the time, could I cross cancel my other fractions, the 400 and the 50? Yes, we could. It's not typically the way it's taught in the nursing program, so I do it with multiplying it out and divide. But yes, you definitely could divide both the 400 and the 50 by 50 and reduce it. So 400 times 4 milliliters is 1,600 milliliters. On bottom, 1 times 50 is 50. That divides out to give us 32 milliliters. So obviously we're getting the same answers for all three of these methods, which is good. No matter what method we use, we should get the same dosage. But it's a matter of which one is easier to use. So let's look at that example where we had multiple things to do in the proportion. So let's say the doctor's order is for 5,000 units. And our label states that 1,000 units contained in 20 milligrams. And of course, constituted, I don't remember, let's do it as 5 milligrams in 2 milliliters. So we start out with the doctor's orders, as always. 5,000 units, we put that over 1. And now we proceed to do our conversions. So our orders are in units. Our first conversion factor here is going to have units on the bottom so that they cancel out. Well, we have 1,000 units in 20 milligrams. That's saying 1,000 units is equivalent to 20 milligrams. So now the units have canceled out. Our only unit now left is milligrams. But we don't want milligrams, we need to get to milliliters. So we keep going. And our next step, we're going to get rid of the milligrams, so they have to go on bottom. We need an equivalency involving our milligrams, and there it is. 5 milligrams equals 2 milliliters. Milligrams cancel out. Now again, we could do some reducing here, and I'm going to, just because I've got the 1,000 and 5,000, I'm going to divide out by 1,000, taking those 3 zeros off. So this is now 5 times 20 times 2 is 200 milliliters. Now on bottom, this is 1 times 5, which is 5. That divides out to give us 40 milliliters. So again, we end up with the same solution we had before, but you note here, it could all be done with the dimensional analysis in one process. I didn't have to go through, find an answer, and then work it through the process again to get to my final solution. Where the dimensional analysis becomes extremely helpful is we start talking about intravenous flow rates. So our IV flow rates are usually set up as a unit of time per hour. For example, let's say a doctor orders 8,000 milliliters to be administered over 16 hours. Well, one way that a flow rate can be represented is in simply milliliters per hour. So if I want to represent this as milliliters per hour, I put my milliliters on top, and my hours on bottom. It is now in a rate of milliliters per hour, but I want to convert it into a unit rate. Remember, a unit rate involves just taking the denominator, the bottom number, and dividing by its amount. So we're going to divide by 16. 8,000 divided by 16 is 500. I was thinking. That's 500 milliliters. 16 hours divided by 16 is 1 hour. So that 500 milliliters in 1 hour is 500 milliliters per hour. I have another example that might be similar to that. Let's say the doctor orders that 700 milliliters be administered over 30 minutes. And we want this in a flow rate of milliliters per hour. Well, we set up our rate, 700 milliliters over 30 minutes. Now note, in both of these problems, this is the doctor's orders here. So we are still starting with the doctor's orders. Now in this case, we don't have the same units. This is milliliters per minute. We want milliliters per hour. So I do have to do a conversion. I need to get rid of the minutes. So since the minutes are on bottom, we're going to put them on top so they cancel out. And we're going to hours. Our equivalency is one you need to have memorized, of course, is 1 hour equals 60 minutes. The minutes cross cancel out. Now, personally, I would do some cross canceling with the numbers here. You wanted to, you could multiply this out and get 42,000 over 30 and divide it out. I'm going to divide out my 30 and 60, both divide by 30, give me 1 and 2. 700 milliliters times 2 is 1,400 milliliters. 1 times 1 hour is 1 hour. If you had done it the other way, you would have 700 times 60 would be 42,000 milliliters. Over 30 times 1 hour is 30 hours. And then you would divide that out. It would still come out to be 1,400 milliliters in 1 hour. So our flow rate is 1,400 milliliters per hour. Well, we might also express IV flow rates in, rather than milliliters per hour, in milliliters per minute. If we're using an electronic infuser, many of those do not allow to be programmed over an hour. They're programmed per every minute. So if our doctor orders that 8,000 milliliters over that 16-hour period of time again, let's set up our rate. 8,000 milliliters per 16 hours. Again, that's just the doctor's order. Right now we have milliliters per hour. We want milliliters per minute. So we have to get rid of the hours. Since the hours are on bottom, we put them on top. 1 hour is 60 minutes. The hours cross cancel. So 8,000 milliliters times 1 is 8,000 milliliters. 16 times 60 is 960 minutes. Now we have the rate units. We have milliliters per minute, and that's what we want, milliliters per minute. We just need to convert this into a unit rate, which is going to be done by dividing by the number, the numerical amount in that second number, which is the 960. So we have 8,000 divided by 960. Give us 8.333 milliliters per minute. When we are in milliliters per minute, we will round to 2 decimal places. So 8.33333 is just 8.33 milliliters per minute. And that's a standard we're just going to keep throughout the rest of the course. Is when we are looking at milliliters per minute, it is rounded to 2 decimals. It can get a little more complicated than that. Our doctor might order 15,000 milligrams to be administered over 12 hours. The label of our container might state 250 milligrams in 20 milliliters of fluid. We want to know what we're going to set this in milliliters per minute, what we're going to set the infuser at to infuse that 15,000 milligrams over 12 hours. Well, as always, we're going to start out with our doctor's order. 15,000 milligrams over 12 hours. That is a rate. But we'll notice here that both of our units need to be changed. We have milligrams per hour. We want milliliters per minute. So we're going to change those milligrams into milliliters. Milligrams are on top here, so we have to put them on bottom to cancel. Going into milliliters, we have 250 milligrams equals 20 milliliters. So the milligrams are gone. Next, we want to get rid of the hours. Going into minutes, 1 hour is 60 minutes. We'll note that the hours are now canceled out. And what we have for units, we do have milliliters on top and minutes on bottom. That's what we want, milliliters per minute. So it's a matter now of multiplying them out and reducing. So 15,000 times 20 is 300,000. That's in milliliters. Over 12 times 250 times 60. Well, 12 times 250 is 3,000 times 60, I believe, is 180,000. Let me try that out. 12 times 250 times 60. And it is 180,000. So we have to divide that out. That is 180,000 minutes. So 300,000 divided by 180,000 gives us 1.666. So rounded to 2 decimal places, we're going to round that to 1.67 milliliters per minute. That is our flow rate. Well, we can add one more step in our level of difficulty here. So let's say our doctor orders let's make this a little easier on ourselves. Let's say our doctor orders 4,000 milligrams to be administered over the next 5 hours. And our label states that this is mixed as 500 milligrams in 40 milliliters. Label also states that this medication has a drop factor of 15 drops per milliliter. Now remember, we discussed that drop factor as being a property of the fluid. If I remember correctly, water is 12 drops per milliliter. So this is a fluid that's slightly thinner than water because it takes a few more drops to create 1 milliliter of fluid. And we are going to be asking now in this case, oops, come on now. For our result, for our dosage to be given in drops per minute. Now, when we're talking about drops per minute, it all depends on what mechanism we're using. If you have some of the modern electronic diffusers, you would round to the nearest tenth of a drop. If you have some of the older manual infusers, you have to go just to the nearest drop. We're going to assume that we have an electronic infuser for now. So we're going to round to the nearest tenth of a drop. So we're going to start with that doctor's order. 4,000 milligrams over 5 hours. And we do have to change both units here. It doesn't matter which one I change first. I can go after the milligrams or the hours first. It really doesn't matter. Last time we went after the milligrams first. This time let's go after the hours first. So I'm going to put hours on top because the hours are on bottom here, so they'll cancel out. We're changing hours to minutes. So 1 hour is 60 minutes. So the hours have canceled out. We're now in milligrams per minute. Well, the per minute is right. That's what we want. So we've got to get rid of those milligrams. Milligrams are on top, so we're going to put them on bottom so they go away. We have 500 milligrams in 40 milliliters. So the milligrams are gone. But we're now left in milliliters per minute. So we need to get rid of the milliliters. So we do another conversion factor with milliliters on bottom. Now we look for a relationship with milliliters. And remember, this rate is also an equivalency. That is saying 15 drops is equal to 1 milliliter. So they're saying 1 milliliter is equal to 15 drops. So the milliliters cancel, and now we do have drops per minute, which is what we want. So we're going to multiply that out. 4,000 times 1 times 40 times 15. Gives us 2,400,000 drops. On bottom, 5 times 60 times 500 is 150,000 minutes. I'm just going to double check that. That is correct. And now we have to divide that out. 2.4 million, 2,400,000. Divided by 150,000 gives us 16 drops per minute. So there's our solution. Now, to be honest, I would have done a little canceling along the way here. Probably at the very least, I would have done this. I can take 1, 2, 3 zeros, 1, 2, 3 zeros, so that I would have had a little more manageable numbers with 2,400 over 150 instead of 2,400,000 over 150,000. We will do more examples with the IV flow rates on Friday. For now, I want you guys to work on page 172 through 173. Problems 1 through 9, the odds. Go over just the constituting solutions and some of the basic dosage calculations from there. Then on page 178 through 179, 1 through 21, the odds. Talks about some of the other dosage calculation formulas, the proportions, dimensional analysis, and stuff like that. So we will pick up from there on Friday. You guys have any questions? Okay, well, you guys have a great day, and we will see you on Friday. Thank you.